right, have your homework handouts out, and just 4 questions for you to find, and some different ways perhaps in which we could do each of these 4 problems.
Watch it, you have 10th graders that don't have it this time.
Nope, yeah. 1 10th grader has it, 2 10th graders have it. All the 11th graders have it.
Did you not do right again? We get at least 2 right.
I think his answers are correct though, so we're good. Again, I don't mind you doing work in your head, but you better be accurate with it if you're going to do it in your head. Or show me the work. And but it does look like his answers are correct. Let's go ahead and take a look at these together. Number 1 from the homework, you had a square, and you were given that one diagonal of the square is 6 inches. And of course indicated as being a square because all the sides are marked as equal, and there's a right angle here. There's really 2 ways that you could find the area. How did you find the area, Quentin?
45, 45, 90.
All right, you said it's a 45, 45, 90. So if this line is 6 inches, which would be represented, then these sides, which would be represented, must each be equal to how big would each of these sides be? If 6 is x squared to 2, then plain old x must be, Ethan, did you do it this way or did you do it a different way?
I don't think I did that one.
You didn't do it this way. That's fine. That's okay.
Yeah, 3 times square root of 2.
3 times the square root of 2. Right. Just divide away the square root of 2. So remember, take say that x squared of 2 equals 6. Divide the square root of 2 away from both sides, and then multiply top and bottom by square root of 2 over square root of 2, which gives you 6 times the square root of 2 over the square root of 4, which, again, you might be able to do that step mentally as 2, and that's where we get 3 square root of 2 for each of the sides all the way around. And then we can go to our formula for the area of a square, Quentin. And so the area of the square would be 3 times the square root of 2 squared. So quick refresher from Algebra 2 for you folks. And I'm going to go show the Algebra 1 method here in just a moment. When you square a radical expression, you square the coefficient to get 9. And then when you square a square root, you get the radicand, which would be 2. The radicand is 2. Like the square and the square root cancel. And that gives you a nice easy answer of 18 inches squared. All right, now, the other way you could do it, Algebra 1 method, is say, well, square means times itself. So you could say, well, that's 3 squared root of 2 times 3 squared root of 2 is 9 squared root of 4, which is 9 times 2, which is 18 square inches. Okay? How many did get the 18 square inches?
No, I just did that. I didn't remember.
Really? Okay. Anyone do it a different way than this? There is another way to do it.
I got 9 times the 4th root of 2.
Okay, remember, when you multiply radicals together, you multiply the radicands, but not the indices. The other way in which you could approach this problem would be to say, well, I know the diagonals of a square are equal, because it's a rectangle. So no, the other diagonal is also 6 inches. And I know that a square is a rhombus. And a rhombus's area could be found, class, using the formula
D1, D2, or 1/2.
1/2 D1, D2. So since one diagonal is 6 and the other diagonal is 6, we could take half of one of the 6's to get 3, and 3 times 6 is 18 inches squared. Either of those methods would have worked. How many thought of rhombus and the diagonals?
I meant to do it that way, I just did it wrong.
Did it wrong, okay, but you understand it now. All right, questions on the first problem. Do we understand it now?
I don't think I have the 6.
You do realize both diagonals would be equal.
I had 36.
Now again, do you realize what I said? You have to remember the diagonals are equal, right?
Sure.
There are things you must remember that we've talked about all year long, or you can't do these. Again, as I've said so many times, you're not allowed to forget anything. Must remember everything as we go over. Fortunately, we've reviewed that a lot. Let's take a look at number 12, and I gave you a right triangle, and then I drew a square on top of the hypotenuse. and I asked, what's the area of the square if these sides of the right triangle are 9 inches and 12 inches? Well, a couple of thoughts come to mind here, Audrey. First of all, anytime I'm looking for the area of a square, I should probably use the formula. When I'm trying to find the area of a square, I should probably use the formula. Right, S squared. SQ equals S squared. Now, we could use the 1/2 D1 D2, except ain't no diagonals in the picture, so probably a bad idea, right? So probably we're going to say that the area of the square is equal to side squared. The problem is, while all the sides are marked with double tick marks, I don't know how big any of the sides are. So then comes a second thought, Audrey. With this right triangle, I know 2 sides, and this side of the square is the only thing I don't know, so Pythagorean theorem. What did you find the length of this side to be using the Pythagorean theorem? 15 inches. Well, now I can find the area of the square, just plug in 15 inches squared, and what did you get for your area? 225 good inches squared. How many had this answer for the second one? Okay, all of us able to figure that one out, Pythagorean theorem. Excellent. Let's take a look at number 3, and if you solved this correctly, you would have found that this is clearly not drawn to scale. How many of you looked at your answer, you looked at the picture like, well, that doesn't match? That's a good sign. That means you probably did it right. All right, if your answer actually matches the picture, that means you probably did it wrong. All right, because the picture doesn't actually match the answer at all, but that's what happens sometimes in life. All right, so we had this trapezoid. Again, this is not drawn to scale. And we had a base of 7 centimeters. We had an altitude which was shorter than the base on the picture, but was 10 centimeters, so you know already something's wrong, okay? Considering this line's shorter, but it's actually longer, and we don't trust our eyes. It only looks shorter, all right? And then we have this longer base, at least it looks longer, but we don't trust our eyes. Turns out it's really shorter. We have this other base down here, and I told you that the area of the trapezoid was 45 centimeters squared. Probably, Chris, what we should start by doing is
writing out your formula.
Which is?
TR equals half of H times B plus B prime.
And then plug in the numbers, right? Unless you don't have numbers, but we do have lots of numbers. So how should we plug in numbers?
45 cm squared equals half of 10 B times B plus 7.
There you go, just plug in the numbers. Now, I can easily take half of the 10 to get 5. All right? Then there's a couple directions we could go here.
I took half of the 7.
You took half of the 7?
I'm not proud of what I did. Okay.
Well, for one thing, first of all, it's in a parentheses with something else. So it's not just a 7, it's a B plus 7, which presents a problem. So unless you did half of B and half of 7, you get half B plus 3.5.
I got the wrong answer.
Yeah, so do you see that half of 10 would be really easy? Or if we didn't want to take half of anything, Ethan, what's the other way of getting rid of this 1/2?
Multiply everything by 2.
Well, everything being both sides, because there's only 2 things. Multiply both sides by 2, so the 2 and the 1/2 gone, and then 2 times 45 would give 90. I think half of 10 makes life really, really easy, though. And so let's roll with that. Let's kind of pick it up from here. Let's suppose maybe we did the easy thing. How many did the easy thing, took half of 10 to get 5? You did. Did you multiply both sides by 2? You didn't do that either. What did you do? You don't know. Do you see what you should have did? All right. Let's see. It's true. We've got honest people in here. Not real smart, but honest. Just kidding. Just kidding. They both had A's on their last test. They're smart. All right. So let's go ahead and take a look back here. Ethan, what might we do to pick up from here? 2 up.
5B plus 35.
There we go. We could either distribute the 5, that's option 1, or, Chris, for redemption,
Or not distribute, divide.
I could just divide the 5 away from both sides. Now, I personally am a big fan of dividing out the 5 because it makes small numbers. When you multiply the 5, it makes big numbers. And I don't like big numbers because they scare me.
I'm a product machine.
But we could go ahead and distribute the 5 to get 5b plus 35. It's not the end of the world, Ethan. We would then... Good, subtract the 35 away to get 5b equals 10, so that b equals 2. Had we divided away the 5, we'd got 9 equals b plus 7, and then subtract the 7 from the 9 to get b equals 2. So either way, 2 centimeters is the length of our base. Clearly not drawn to scale. I did notice, Quentin, you had the 2 centimeters. Anyone else get 2 centimeters?
I was
for this?
really close.
Okay, Ethan, you did as well. The rest of us, questions?
I got 2 and 4 7.
Well, yeah, if you took half of 7. All right.
That was so weird. Like I was like,
I felt like this was pretty straightforward, and this is what our 8th graders would do. So I'm a little mystified where 11th and 10th graders struggled with an 8th grade concept. Now, the first 2, those were 11th grade. Our little ones aren't doing that. But number 3 was pretty straightforward without questions. We understand it now?
Yeah.
Good. All right, let's go on to number 4. And here I gave you a triangle, XYZ, and I told you that the triangle was equal to this square, ABCD. So triangle equals square. I wanted to know the length of one side of the square if the base of the triangle is 9 inches and the altitude was 8 inches. Genesis, what might we do to solve this one?
I tried to do the Pythagorean theorem on the triangle.
Do you see that don't work too good because it's not a right triangle? All right. So what might we do instead? Given the base of the triangle and the altitude of the triangle.
Use one of the formulas.
Yeah, specifically which formula would be the ideal one to use?
Right triangle equals.
Oh, is this a right triangle, Genesis? No, don't use that one.
T equals 1/2 h.
Yeah, let's use the t equals half bh. Let's go ahead and find the area of the triangle. We have everything we need to find it. Go and clear your desk, Bracken. We have everything we need to find it, so let's plug in the numbers here and walk me through here, Genesis.
T equals 1/2 8 inches times 9 inches.
There we go, or vice versa technically, but it really doesn't matter because they're being multiplied. And work that out. What would you get for the area of the triangle? 36 inches squared. All right, so that's the area of the triangle. How many did that first step? You found the area of the triangle. Good. Now, Genesis, that's the triangle's area. What do we know about the square? Oh, yes, we do. Well, we do know it's a square. There's something else we know about the square. The very first line of the problem says,
triangle ABC equals square ABCD.
oh, sorry, that should say XYZ. Triangle XYZ equals square ABCD. In other words, they're equal. What does equal mean?
That they share the same, well, they have the same area.
They have the same area. So if the triangle's area, Genesis, is 36 inches squared, then the square has an area of 36 inches squared, correct? Not a perimeter, but an area of 36 inches squared. So, to find the length of the side, I would want to use what formula?
Square equals side square.
And since I know that the area is 36, I can plug that in for SQ. And so to find S, I just need to take to get a length of a side to be 6
inches squared.
just plain old inches, right? Because area is inches, lengths are inches squared, units squared for area, and then plain old units for lengths. So side is 6 inches. How many got? 6 inches for the length of the side. Questions on that? Does that make sense now? All right, questions on the handout. All right, go ahead and clear your desk except for a sheet of paper, a pencil, and a calculator. One clean sheet of paper, a pencil, and a calculator. Everything else away. First and last name at the top of your paper, along with today's date, which is 5/4/21. Or you put Star Wars Day. May the 4th be with you. Always. Particularly right now, if you believe in that sort of thing. Or it's just fun to joke about. First and last name at the top of your paper, along with today's date, May the 4th. 5/4/21. 4, 21. And this is quiz 39B. Quiz 39B. Even though some of your quizzes will say, wait a second. Hold on, Houston, we have a problem. I think this happened last time too, but I think the quizzes got mixed up for some of these.
We have 8.
Are you good? Your whole row's good? You have 8 questions and a bonus? Okay, good. Well, it seems like I caught the bad ones before I handed them out. Okay, there's that, there's that. Yeah. I guess I got my quizzes mixed up last time. I put some of them in the wrong stack, and now some of these in the wrong stack. All right, pretty straightforward. There are 8 problems. I would recommend drawing pictures for most, if not all of these. Definitely write some formulas and work them out. There is a bonus for you as well. All right, you may begin. Be sure to use your quiz copy as a cover sheet. As always, don't allow yourself to get stuck on a particular problem. Get as far as you can. If you just realize, I don't know what to do next, move on, come back to it. Just another minute or so to be finishing up, putting down final answers. I need to go and collect those up from you at this time. I'm going to collect those from you.
I still only did 3 before 2.
Okay, I see the number in there. Soon. All right, go take out your notebooks if you would. Please turn to the Theorems Corollaries section. Theorems Corollaries section of your notebook. Theorem 72. Theorem 72. It says this. If two triangles have an angle of one equal to an angle of the other, if two triangles have an angle of one equal to an angle of the other, that's not a lot of information, is it? Just one angle of one happens to equal an angle in the other. Okay, that's not that much knowledge. That doesn't even make them similar, right? Okay, so if two triangles have an angle of one equal to an angle of the other, then their areas are to each other, if two triangles have an angle of one equal to an angle of the other, then their areas are to each other as the products, then their areas are to each other as the products of the sides which form the angles. Their areas are to each other as the products of the sides which form the angles. If two triangles have an angle of one equal to an angle of the other, then their areas are to each other as the products of the sides which form the angles. Once you have that down, go ahead and turn to the Proofs of Theorems Corollaries section. Proofs of Theorems Corollaries section. And at the top of a new sheet of paper, go ahead and put Theorem 72. Then if you would, go ahead and draw some triangle. Really doesn't matter how you draw it, though try not to make it look isosceles or anything special, and let's call it ABC. And I want you to note the measure of your angle A. It doesn't have to look exactly like mine. Just notice how big your angle A is. Then if you would, try to duplicate the angle, but not the length of this side. Maybe make the triangle look considerably different. So while one angle may be equal, the rest of the triangle looks nothing the same. And I'm going to call this triangle XYZ. All right, so I've got two triangles, ABC and XYZ. They're definitely not similar, but they do at least have this angle A equal to that angle X. And if it doesn't look perfect, and I'm beginning to look at mine and think, I don't think that's very perfect, doesn't matter, we don't trust our eyes anyway, right? But we know one angle equals another angle, and that's all we know. So, given triangle ABC and triangle XYZ with angle A equal to angle X. That's all we know, is that one angle of one equals one angle of the other. Once you have that down, well, let's get at what we're trying to prove. It said to prove that if an angle of one triangle equals an angle of another, then the areas are to each other. So that means we're going to make a ratio of the areas. The area of triangle ABC, that's capital T sub capital ABC, is to triangle XYZ, that their areas are to each other as the products of the sides forming the angles. So in other words, if I were to multiply side AB times side AC, I could compare that product to the sides XY times XZ. Prove that the areas are to each other as the products of the sides forming the angles. That's what we're going to try to prove. Once you have that down 2 columns, statements, reasons. Two columns, statements, reasons. And go and get down your first statement and your first reason. And normally, it's been a little while since we've done a proof, but normally, Kendall, we begin a proof by asking if we have any claim statements. No, we don't have any claim statements. Okay, so no claim statements. So then, Kendall, once we've gone through all our claim statements, even if we have no claim statements, then we would ask ourselves, what am I trying to prove? I'm trying to prove that 2 areas are being compared. Now, we've seen this before, but we didn't have T sub ABC is to T sub XYZ, but rather, class, T is to T prime as, class,
Side is.
way to go 10th graders. Once again, saving the day. T is to T prime as BH is to B prime H prime. This is coming back to the rest of you now, right? Areas to area as base altitude is to base altitude. That's at least a start. At least that's something, right? At least it's areas to areas to a product is to a product. That's kind of what I'm trying to prove here, right? But that's got altitudes. I don't got altitudes. Chris, thoughts?
You know I love doing this. Auxiliary lines.
Let's do specifically which auxiliary lines, Chris?
The altitudes.
The altitudes, of course, that's what we're missing. So let's go and draw the altitude, CD, and ZW. And number 2, now we can't call them altitudes necessarily, but an altitude means, class,
A line drawn from the vertex angle to a certain point on the line.
well, not to a certain point, but perpendicular. So let's draw perpendiculars, and we'll actually call them altitudes in a moment. So let's say draw CD and WZ perpendicular to AB and XY respectively. Draw CD and WZ perpendicular to AB and XY respectively. Because I know, class, that from a point,
One and only one line can be drawn to a point
perpendicular to a given line. There we go. From a point, in this case the point C and then the point Z, from a point, only one perpendicular may be drawn to a line. We didn't have any other perpendiculars already there, so we're going to say that's the perpendicular we can draw. Now, since they are perpendicular, by definition, class, that makes these lines our altitudes. So number 3, we can say that, well, Chris?
Line CD and line ZW are altitudes.
CD and WZ are altitudes. Based on?
Definition of altitude.
There we go. Definition of altitude. We could say of a triangle if we wanted to be even more specific, but I don't know if we necessarily even need that. They're altitudes. Definition of altitude. Okay, well, that's what we wanted, right?
Now we have some claims.
Now we can do something here with this whole thing, right? We can say that, but we're not going to say T is to T prime. let's go and use these two triangles specifically. So let's say that triangle ABC is to triangle XYZ as base times altitude is to base times altitude. Genesis, how would I put the lettering in here? Triangle ABC is to triangle XYZ as or AB times CD is to, there we go. Triangle ABC is to triangle XYZ as AB times CD is to XY times ZW. And that's because we proved that the areas of two triangles are to each other as the products of their bases and altitudes. The areas of two triangles are to each other as the products of their bases and altitudes. Now look closely at what we put in number 4 and look at what I'm trying to prove. They look really close, Audrey. Thoughts? Compare statement 4 to what I'm trying to prove. The only difference and this ratio right here and this ratio right here are different. Agreed? All of us agree? All right, if somehow we could make those two ratios equal to each other, then I'd be in business. Wait a second. If I could make those ratios equal, Jamie, what do we call equal ratios?
Proportion.
A proportion. So we all understand, if I could say that CD to ZW equals AC to XZ, right? If this were true, class, I would take this out and plug that in its place and I'd be done with the proof, right? So in other words, I want to find a way to prove that that's true. Do we see the analytics there? How do we generally prove lines proportional, Jamie?
Similar triangles?
Yeah, but I don't have similar triangles, do I?
Like have equal angles.
I have one set of equal angles. And we expressly stated, class, that these two triangles were not similar. But Jamie...
Yeah, to use like a perpendicular and a right angle.
It's not about these triangles, it's about which triangles, Jamie?
A, B, C, and X, W, Z.
And because I have perpendiculars, I will have
Right triangles.
right angles, which give me
Right triangles.
right triangles. So yes, the big triangles are not going to be similar, but with the altitude drawn, this portion would have to be similar, right? Oh, by...
CSSTP.
You got ahead of yourself there.
Oh.
How would I be able to prove these similar here in just a moment?
AA.
Angle. Get the right angles equal. We've got angle. So let's go about that then. Number 5, Ethan. Before we can just jump in and say, oh yeah, I've got angle. There were some thoughts that led up to that. What were the initial thoughts?
Angle D equals angle W.
Because they are.
Right angles.
Where does it say the right angles?
You just say it.
We have to say. So that's where we want to start, right? We want to start by saying that they're right angles. In fact, let me number them 1 and 2, because technically D would be anyway. So number 5, we should state, Ethan.
Right angle 1 and 2 are right angles.
And we know they're right angles because.
The definition of right angle.
And because they're both right angles, then Ethan, you said we could say
Right angle 1 and angle 2.
because.
All right angles.
And then Jamie, because the right angles are equal, you said.
Triangle ADC equals triangle.
Not equals.
Is similar to triangle XWZ.
Good job on the lettering there. Reason.
Angle.
And because the triangles are similar by angle, then in number 8, we can say, Audrey. Why did I want the triangles similar? Right, so let's put this then down here in number 8. Once the triangles are similar, triangle ADC and triangle XWZ are similar, then that proportion, CD is to ZW is AC is to XC, is true by, right, corresponding sides of similar triangles, that's what we just proved, are proportional. And once I've got this truth, then I can simply take this ratio, right in there for that ratio by class substitution. So number 9, I've got what I want to prove by a simple substitution. And so now we've proven that if just one angle equals one angle, that the product of the sides is to the product of the sides as the areas are to each other. Areas to areas, product is to product, if you will. Give you a moment to finish copying that. And questions on the proof as you finish copying. Does it make sense? Not asking if you would have necessarily thought of this proof, because it took a bit of creativity perhaps, but you understand kind of the thought process through? Any questions at all? Tell you what, we won't take time to prove it, but let's go and get down Theorem 73 in your notebooks now. So back to the Theorems Corollaries section. And now let's delve a little deeper. These triangles weren't similar, correct? But what if we did have similar triangles? Theorem 73 says this: the areas of two similar triangles, are to each other. The areas of two similar triangles are to each other as the squares of any two corresponding sides. The areas of two similar triangles are to each other as the squares of any two corresponding sides.
Can you say it again?
The areas of two similar triangles are to each other as the squares of any two corresponding sides. Here's kind of the thought. We'll talk through the proof very briefly. If they are similar, then we know we have an angle equal. In fact, we have 3 angles equal respectively, don't we? Let's just take angle X, A and X again for sake of illustration, but this time they're similar. Well, then that means, as we just proved, if at least one angle is equal to one angle, area is to area as the product of these two is to the product of those two, right? But what do we know about the ratio of any two corresponding sides of similar triangles, class? They're proportional, right? Corresponding sides are proportional, which means that AB is to XY as AC is to XZ, correct? Which means I could take AB to XY, plug it in right here where AC is to XZ, and now that AB to XY is AB to XY. Or in other words, AB squared to XY squared. And for that matter, I could have plugged in any sides for both of them, correct? I could have taken BC to YZ and plugged it in, and then I have BC squared to YZ squared, right? With the sound effects, and that's very important. Do we understand how Theorem 73's proof works, even though we didn't take time to write it out? And then that's going to lead us tomorrow into something significant, but we don't have time to get there today. All right, your homework for this evening, if you were watching on YouTube, would be page 17 of the second semester handouts. Page 17 of the second semester handouts. But for those in here, you'll just do the handout that I give to you. Just 3 problems, on this handout this time. Just 3 problems. So the handouts are getting progressively shorter. Probably because the problems progressively take more thought to complete. All right, we'll take a look at this tomorrow. We'll take a look at your quizzes tomorrow, and then we'll get to that Theorem 74, which is where we've kind of been headed this whole time. Have a wonderful rest of your day, and you are dismissed.